This is third module of theory of elasticity. So, in this module we will basically learn what is constitutive equation or constitutive relation of a material. So, not only in this module, in the next module also we will discuss constitutive relation. Now, to start with, in the previous module you have learned these quantities, for instance stress, strain, and specifically the Cauchy stress and traction and strain displacement relation, everything you have learned in the previous module. Now, probably also you have learned that stress, this is a tensorial representation. So, sigma we represent it in this way, and then in void notation or in a vector form we represent in this way, that strain similarly also we represent in a tensorial notation epsilon, and then in void notation in a vector form. Remember one thing, that this is 2 EXY is actually the shear strain and the strain tensor strain. So, these quantities we have learned in the previous module. Now, it is also important to note here that this stress matrix is symmetric matrix. So, here this is sigma is actually sigma transpose. So, similarly strain matrix is also a symmetric matrix. Now, how these stress matrix or strain matrix become symmetric, we will learn after these two modules, and specifically the stress becomes symmetric due to the balance of angular momentum. So, we will learn these things in a fifth module. Right now we know the stress, strain, and probably also you have learned that strain displacement relation, which is half of del u plus del u transpose. So, probably this thing you know now, and this del u is the displacement gradient, and then half of plus del u transpose, and half of this is known as the strain. So, this is linear strain. What do I mean by linear strain? Because this relation is essentially linear. So, relation between the displacement and strain is linear. So, this is small strain or linear strain theory, and so we do not comment about anything on the stress. So, now what it comes after this is the balance law. So, any body which is essentially deforming, suppose there is a body, the body is deforming from initial configuration which is omega 0 to another configuration which is omega omega. So, this is a body. So, you know what is the concept of traction. So, here some due to load is given, some force is given, some boundary condition is given, and something is given to resist the motion, some point. So, this body deforms finally to a current configuration, and with the action of this traction force. Now, this deformation is actually what do we measure about this deformation? So, essentially we measure we are interested in knowing what is the deformation, that means what is the displacement. In true sense, it is ux, uy and uz say. So, we are interested in knowing the displacement vector. So, if I consider this is a 3-dimensional plane, so x, y and z coordinate system. So, this is a 3-dimensional plane. Now, this we are interested in finding out this displacement. Now, to find this displacement, what we have done is initially we relate this displacement with the another quantity known as strain, and these strain components are given or we know the strain components. Now, similar to that, we also defined stress components. So, now important thing is that how this stress and strain is related we will know in this module. Now, before that I want to emphasize this, that after knowledge of strain, displacement and knowledge of stress, we can formulate the governing equation or the equilibrium equation of the body. So, that body goes from undeformed state to the deformed state, and which is essentially the force balance equation. So, we can write its differential equation, which is of this form. We have not seen this earlier, but just to mention this, that this del dot sigma is plus b equals to 0. Now, this is over the domain omega 0 and with proper boundary condition, So, boundary condition could be a traction boundary condition. If you have if you remember that boundary condition can be done in terms of some displacement or also known as Dirichlet boundary, and traction or the sigma n in the traction boundary. So, this with this boundary condition, and this is a static problem. So, there is no inertia term. So, the difference between static and dynamic problem is the inertia term. So, this is a static problem and B is the body force. So, this will discuss in the 5th chapter or 5th module. Now, you see we are interested in finding displacements, but our governing equations are in terms of stresses. So, we need to know how stress is related to the displacement. So, that means we know strain, how displacement is related with the strain, and this equation is linear, as I said earlier, because linear means the relation these are all linear terms. So, this is linear strain tensor. We know this linear strain tensor, and now how to relate displacement with the stress? We need to relate stress with the strain probably. So, probably you have heard this Hooke's law, or stress is proportional to strain, the linear elastic case, where essentially if you have probably this kind of spring force if you apply, and if there is a stiffness K, so this force is proportional to delta, the displacement, and then F equals to K delta, right. This probably you have learned from your basic mechanics concept. Now, if we look back or if we generalize this thing, probably you have also learned that stress is proportional to strain in 2 dimension or 3 dimension. So, now the essence of this discussion is that we need to relate stress and strain. Now, here if I define strain as above, which is half of del u plus del u transpose. Now, this implies that this problem is a linear strain problem or small deformation problem or small displacement problem. This kind of problem is geometrically linear. That means, the strain displacement relation is linear. So, we say this is geometrically linear problem. Now, certainly when this strain and displacement relation is not nonlinear and is not linear, so it can be geometrically nonlinear also. For instance, we will define green Lagrange strain is something the later part of this course. So, geometrically nonlinear problem, this is a strain in which the strain displacement relation is nonlinear. So, this is one possibility. So, we are not discussing this kind of problem here, where there is a geometrical nonlinearity present. Now, when we start relating strain with the stress, so we need to assume or we need to know how material behave. So, essentially if I load a steel beam, or if I load a concrete beam, or if I load a wooden beam, material will deform in a different way. So, to identify or to know how material will behave, we need to know how stress and strain relates for this material. For instance, we assume linear stress strain relation or Hooke's law, where we say that stress is proportional to strain. So, that means when we say sigma is proportional to epsilon, right, and the proportionality constant also, you know, for one dimensional case it is Young's modulus. For three dimensional case, appropriate definition of Poisson's ratios, or the ratio between transverse strain and the longitudinal strain. So, these things we know from our basic knowledge of solid mechanics. Now, this relation when sigma is proportional to strain, this relation is known as linear, right, because it has a only constant coefficient. So, the proportionality constant becomes Young's modulus, or in a multidimensional case it is known as the constitutive matrix. So, essentially where is the need for this constitutive relation comes here. So, in our governing equation, or what equation we want to solve, that for a different material this constitutive equation will be different, right. So, the constant proportionality constant here, for instance, if I write it in a just simple manner without knowledge of these tensors. So, this if I assume as a matrix, or assume as a vector, and this assume as a vector. So, this becomes a matrix, so which is Cij, right. So, this matrix is constant. So, there is no it is not dependent on any other thing. So, this is a constant matrix, and this relation is known as the Hooke's law, or the linear elastic material. Represents the material behavior of the structure, or materialistic behavior of the structure is linear. Now, certainly this is important where if we want to solve or find out the displacement, because this is the connection of sigma with the epsilon, or the sigma epsilon relation. So, we need to substitute this relation here and then solve for displacement. So, this is overall the process. Now, another important thing is that this relation sigma is proportional to epsilon, or stress is proportional to epsilon, this we are assuming, or we are discussing those material which follows this relation. So, this is certainly linear relation. So, that can be nonlinear also. That means, sigma may not be directly proportional to epsilon. So, there is a relation between sigma and epsilon which is nonlinear in terms of strains. So, there that kind of material, or that kind of relation, we will say this materially nonlinear. So, materially nonlinear. So, now we learned two things. One important thing is that geometrically linear problem and materially linear problem. So, we are discussing geometrically linear problem and materially linear problem. So, the nonlinear, when we separate it out from a linear problem, nonlinearity can be of two types: geometrically linear problem or materially nonlinear problem. Now, why do we need to know stress strain relation? Because we are interested in finding out u x, u y, e z or the displacements. So, this is the background on which we are studying. So, in this module basically we will study this relation or the stress strain relation for a linear elastic material. Now, the word linear elastic here is implied that it is geometrically linear problem as well as materially linear problem, right. So, now if we proceed, so naturally the stress strain relation will be different for a different material. For instance, if we are talking about steel, the stress strain relation will be different. If we are talking about concrete, the stress strain relation will be different. So, here is essentially the material behavior comes into picture. So, essentially constitutive relation characterize the physical property of the material or how material behaves. So, essentially it relates stress versus strain. So, now another important thing probably we have discussed in the first lecture of this or the introductory lecture of this course, that elasticity. So, elastic solids can recover its configuration upon removal of loading, but unloading path has to be same with the loading part. This also I have discussed with an example. That means, if loading and unloading path are different, then material may not be elastic. So, in case of this kind of material where loading and unloading path are different, so it loads here and the unloading path here. So, this is not a elastic material. So, this is a strain and this is stress. Now, so this kind of material we are not talking about. So, loading and unloading path has to be same, and this implied that there is no change in the energy, because if we know from our strength of material or solid mechanics concept that area under the stress strain curve is the strain energy, right. So, we will discuss this also in detail. Now, elastic solids do not include rate or history effect. So, the path is important, but the effect on this, how this path is taken and what the memory effect, or there is no memory effect on the elastic solid. This is also well understood by us. Now, if stress is linear function of strain, then it is linear elastic solid. Similarly, it is strain is linear function of displacement, it is geometric linearity. So, under small deformation, that means when the deformation or the displacement of the body is small, then wood, ceramic, metal, etc. shows some linear behavior. Now, probably all of you have done some test on the uniaxial solids, where we just carry out simple tension test. If you remember that one rod we tested in a laboratory, where we see cup and cone behavior of the rod, and in a universal testing machine we obtain stress strain curve. So, essentially how stress is found out? Stress is found out by dividing the load recorded by the area of the specimen. So, this is essentially how we found out stress, and strain is found out by measuring the change in length. So, that is the basic definition, and with the help of strain gauges we find out strain. Now, so this is a typically stress strain behavior or stress strain curve. For instance, if I just see the mild steel have a very distinctive material behavior. For instance, this portion is essentially linear. So, now from here this is some nonlinearity or curve behavior. So, then it reaches some point and then suddenly it drops to another point. suddenly means that is a small increase in strain from here to here, small increase in strain, suddenly the stress decrement happens largely. Then it follows a straight path, which is then after that it again gains stress, or it takes stress, and then it follows somewhere after it reaches some maximum value, and then also this is an ideal stress strain diagram. So, a material may not follow this, but this is a ideality. So, we will discuss what are these things. So, for instance, different material behave in a different way. For instance, if we draw the steel, it looks like this. If we do the cast iron, it will be just after there is no distinctive yield point or something, and then suddenly break. If we press aluminum, then it may looks like this. So, this is the specimen we test it in the laboratory. Now, so A is the proportional limit. So, here if we see that the proportional limit, what this proportional limit means? Proportional limit means that stress strain relation is linear. So, that means stress is proportional to strain, and the slope of this also we know, the Young's modulus. Now, B is the elastic limit. You see from A, or specifically from point A to point B, the elastic limit is point B. So, that means from point A to point B, material is not behaving linearly. That means the stress strain relation is not linear. So, it may be nonlinear. Now, after this elastic limit, that means if we release at point B, the material will, if we release the load at point B, so material will come back in the same path. So, this elastic limit, material will come back in the same path. Now, C, D are yield points. So, for a mild steel, this is a ideal mild steel stress strain diagram. The point the top portion here is known as the yield point, the upper yield point, and point then after sudden increase of strain, we observe that there is a sudden drop of stress. So, this is known as the lower yield point, and this is probably specific for the mild steel. And then we observe a yield plateau, or where stress does not change much, and then with the increase of strain. So, after that it again takes stress. So, it reaches to with the increase of strain, it increases to ultimate stress. Now, once it reaches to ultimate stress, then with the increase of stress, necking and all those things occur, and then it goes to failure. So, the failure or the rupture occurs. So, this is a overall behavior of a stress strain curve. Now, this probably we know from our laboratory experiment. Now, so naturally steel and aluminum will behave in a different way. So, this yield plateau or the some elongated plastic zone is no, if the material is having the elongated plastic zones. So, that means if we just have these elongated plastic zones here. So, this is known as the yield. If it shows a plastic zone a significant amount, then this kind of material is known as ductile material. But on the other hand, if you remember from the previous curve that we observe for a material which is essentially fails here. For instance, this is a cast iron. So, this material suddenly fails here. So, and this is known as the this kind of material is known as a brittle material. For instance, the concrete, if you draw the stress strain curve of concrete, that will also look like this, and so this kind of material is known as the brittle material. Now glass also a material, so there are very less plastic zone, and some material don't possess yield point, so that I have explained. So that may not be, so in the mild steel we observe a distinct yield point. So in case of different other materials we may not observe yield point. So brittle material shows sudden failure, but ductile material elongates sufficiently before failure. This is well understood from our, if you remember, we use concrete. So concrete is a brittle material, so so it fails suddenly. So that is why we don't prefer concrete in several structure. So for ductile material, cross sections are reduced upon loading beyond this yield point. Now there is also called something called true stress. Probably we know this is which is the stress we measure is the based on the current area. If we measure the load versus current area, then we call it true stress. So true stress will be, if we plot the engineering stress and the true stress, that curve will be different, because from here actually the area is also changing. So the amount of stress which is engineering stress, which is always based on the undeformed area. So since the area is changing, so the quantity will be higher and the true stress will be this. So engineering stress versus true strain curve. Now for most of the material, however, the initial stress strain curve, though for concrete the initial stress strain curve is not very prominent. So for most of the material, initial portion of the stress strain curve, say this for this material up to this, so this stress strain curve is linear, and the constitutive model for this is the Hooke's law, which is sigma c epsilon. Now this kind of material we will be discussing here mostly of linear these materials are called linear material. Now what we will do here, we will just learn something without proving anything or without knowing how it comes initially, and then we will prove each things separately. So if we write the, since we know that linear combination or the linear stress strain relation, so naturally each stress will be related with the strain with a linear coefficient, and which is C11, C12 and Cc up to C66. So in a matrix format, this is the form. So this relation is known as the Hooke's law for a general three-dimensional body. Now what we will do here is essentially okay. So here in the tensorial form we can write it sigma ij, or the initial form we can write it in this manner, and in a tensorial form we can write it in this form, C double colon epsilon. So essentially C is a fourth order tensor, C is a fourth order tensor, and sigma and epsilon are second order tensor. So number of components in this fourth order tensor will obviously 81, because 3 to the power 4, and so as stress tensor it is 3 to the power 2, so 9, and from the symmetry we get the 6 independent stress component. So based on the property of these coefficients, or how these coefficients are arranged, or based on the property of this matrix C, we can have different material. If the material possesses single plane symmetry, it is known as the monoclinic material. If it is having 3 plane of symmetry, then we say it is a orthotropic material, and we will see the 9 independent components. Similarly, for a transverse isotropic case, we will have 5 independent components, and for the isotropic case, which we know from our solid mechanics or strength of material knowledge, will have 2 independent components, and these 2 independent components are essentially Young's modulus or and Poisson's ratio, or it can be shear modulus or first Lamé constant. So these quantities essentially we know from our previous knowledge. Now, what we will do here is essentially we will start with this and then we will derive each of the material. For instance, we will derive monoclinic, orthotropic, transverse isotropic material considering the different symmetries. But before that, let us see how for an isotropic material how stress strain relates and what is the stress strain equation. Now, there are another important thing we have to remember here. A material can be a homogeneous material. Probably this we have discussed in the first lecture, that homogeneous means if there is a, suppose there is a body, so this body if I measure or if I find out the material property at this point, and if I find out at this point, if the material properties or the Young's modulus at all points are same, then we say the material properties are homogeneous. Now, this is a two-dimensional body. So, suppose at this point the axis is here. So, this is x1 and x2. So, if the material Young's modulus along x1 and x2 are same, then we say it is an isotropic body or isotropic material. So, material property is same along any direction. So, Poisson's ratio similar to Young's modulus, Poisson's ratio have to be same. So, now this is very important distinction between homogeneous and isotropic material. So, it is very important to distinguish between heterogeneity. So, isotropic means, so material property in all direction will be same. So, now if you remember the isotropic tensor or the isotropic elasticity matrix, it is it looks like this. So, we will derive this equation, but let us know this equation first. So, this is known as the first Lamé constant, and then this is the second Lamé constant or the mu shear modulus. So, and how lambda is related to Young's modulus and Poisson's ratio, this is the relation. So, we will learn this or will essentially prove this. So, the essence of this discussion is that isotropic modulus, we will assume this isotropic modulus will have two material constant, which is E and nu, Poisson's ratio. This is from our previous knowledge. Now, if I just take this relation, the generalized Hooke's law, so which is sigma ij is lambda epsilon kk. So, in a tensorial notation 2 mu epsilon E ij. So, if I write in tensor form or the coordinate independent relation, so which is essentially lambda trace of E I plus 2 mu E or epsilon. So, this is a second order tensor, this is a second order tensor, and this is a second order tensor. So, now this relation, if I write it in a void notation, which is sigma x, sigma y, sigma z, so it looks like this. So, this is Hooke's law for a material. Now, if we now invert this relation, and there is a reason why we are doing it here. So, if we invert this relation, and we will get the another expression or which relate strain to stress. So, if we invert after doing some calculation, if we invert this relation, so it looks like this. So, this is the essentially the strain how it relates with the stresses. So, if I write this in a form in a component form, so this will be sigma x, sigma y, sigma z, and so strain. So, if I have stress, then I can calculate the strains components. So, the basic purpose of this in the next lecture, we will understand what this means actually, what is the physical meaning of this Young's modulus or the Poisson's ratio, or we will define some quantities like bulk modulus, and these quantities, what is the physical meaning. So, material, how it means to us, a material is given to you, or so you are as an engineer very interested in knowing what is its material property. So, that is our motivation of studying this, and in the next lecture we will essentially understand what is the physical meaning of this isotropic material constants E nu, right. So, I stop here today. So, in the next class we will see the physical meaning of the isotropic elastic constants. Thank you.